Markov chains, their transition matrices are many and varied. We'll be working with a restricted class of them that has the main properties and is rich enough for our purposes. Compare these two transition matrices that I've drawn here. They differ only in the line, the row corresponding to the starting point of B. Everything else, every other row is the same. And let's start by looking at the one on the right first. Suppose you start at the state A, then where can you go? Well, you can go to B, and then from B you're just sent right back to A, so there you are, and you're at A again, and then you can go to B and you're sent back to A. Essentially you cycle around between A and B. If you start either at A or at B, you cycle around between A and B, and you can never get to C, and you can never get to D. This chain clearly is going to have some irregularities in terms of long-run behavior, in the sense that the starting point does matter. If instead you look at the chain on the left, then you can get from anywhere to anywhere. Let's exhibit a path that starts, where should it start? Why don't we start at B? And let's see that we can actually get to every state. So from B, why don't we say, can we go to C? Yes, we can go to C. From C, let's go to D. Now, once we've got to D, the only other place we can go is C, so we head back to C again. And what's the state that we haven't picked up yet? We haven't picked up A, so from C we can get to A. C is a very convenient state because it takes you everywhere. And only one question remains now. From A, can you get to B? Sure you can. So what you've done is created a loop. It is a loop that starts at B and comes back to itself, having visited every other step along the way. This path has positive probability. And this means for the chain on the left-hand side, it is possible to get from any state to any state. And such chains are called irreducible. If you look on the right-hand side, you have your own private little chain here consisting of A and B, and then some other stuff going on. In some sense, you can reduce that chain. We will be focused only on irreducible chains, chains where there are no groups that don't talk to each other.